Find somewhere comfortable. You don't need to follow any of this closely. You don't need to remember a single word. Just let the sounds arrive, the way water arrives at the base of a slope, without effort, without hurry. We are going somewhere slow tonight, somewhere deep and quiet and old. If today was hard, you can set it down now. If your mind is still turning over something that happened, some conversation, some worry that has been sitting in your chest since this morning, you don't need to resolve it tonight. You don't need to resolve anything. The thoughts can pass through the way water passes through stone. Patient, unhurried, going where they have always been going. Tonight we are following water. Not the water in rivers you can see, not the water that catches light and makes sound as it moves over stones in the open air. We are following the water that goes down, the water that disappears into the earth and keeps moving in the dark, through passages no sunlight has ever touched, through rock that has been slowly giving way for longer than our species has existed. This is a journey that takes, in places, 10,000 years. We have all night. We are in no hurry at all. Close your eyes if they aren't already closed. Let your body become heavy, and let the words be nothing more than a quiet company as you drift. Picture a single raindrop, not a storm, not a weather system, not the grey weight of clouds gathering over a hillside. Just one drop, the one that falls from a particular cloud at a particular moment, somewhere over limestone country, the rolling, pale grey uplands of Yorkshire perhaps, or the dry scrub hills of Mexico's Yucatan Peninsula, or the karst plateaus of southern China, where stone towers rise from flat plains like the remnants of something vast and dissolved away. This drop begins its life not in the cloud itself, but in the space between cloud and ground, because the air it falls through is already doing something to it. The atmosphere contains carbon dioxide, not very much, roughly 4 molecules for every 10,000 molecules of air, but that small amount is enough. As the raindrop falls, carbon dioxide dissolves into it. Water molecules and carbon dioxide molecules meet, and when they do, something new is made. A water molecule is 2 hydrogen atoms bonded to 1 oxygen atom, arranged at a slight angle, not in a straight line, but bent, like an open pair of arms. This bent shape gives the molecule an uneven distribution of electrical charge. The oxygen end pulls electrons toward itself more strongly than the hydrogen ends do, leaving the oxygen side of the molecule slightly negative and the hydrogen side slightly positive. This is what chemists call a polar molecule, a molecule with a definite positive end and a definite negative end. Carbon dioxide, by contrast, is a straight molecule, 1 carbon atom flanked symmetrically by 2 oxygen atoms. On its own, it has no net charge imbalance, but when it meets water, something interesting happens at the level of individual atoms. The polar water molecule can interact with the carbon dioxide molecule, and the result is carbonic acid. The chemical name is H2CO3. 2 hydrogen atoms, 1 carbon atom, 3 oxygen atoms, rearranged from the original ingredients into a new configuration. It is a weak acid, meaning it does not release all of its hydrogen ions at once, the way a strong acid would. But it releases enough to make the raindrop measurably, meaningfully acidic before it has even touched the ground. The pH of pure water, a measure of how acidic or alkaline a substance is, on a scale where 7 is neutral, lower numbers are acidic and higher numbers are alkaline, is exactly 7. Clean rainwater, carrying its dissolved carbon dioxide, has a pH of around 5.6. That is mildly acidic. Not corrosive in the way that industrial acids are, but chemically active in a way that will matter enormously over geological time. Now the drop reaches the ground. If the surface is bare rock, it might run off. But here, on our limestone hillside, the surface is soil, and the soil is a remarkable thing. It is not simply ground-up rock. It is a living matrix of mineral particles, fungal threads, decomposing organic matter, and the metabolic activity of millions of microorganisms, bacteria, fungi, nematodes, springtails, all of them respiring, all of them releasing carbon dioxide as a byproduct of breaking down organic material. The concentration of carbon dioxide in the air spaces within soil can be 10 to 100 times higher than in the atmosphere above. So as our raindrop enters the soil and begins to move through it, it absorbs still more carbon dioxide. The carbonic acid concentration in the water rises. The water becomes more acidic still. Its pH might drop to between 4 and 5 in a particularly active, organic, rich soil. And now it is ready to do something remarkable to the rock beneath. Limestone is calcium carbonate. It is made of calcium ions, calcium atoms that have each given up 2 electrons, leaving them with a positive electrical charge, and carbonate ions, each of which is 1 carbon atom bonded to 3 oxygen atoms, carrying an overall negative charge of 2. These oppositely charged ions attract each other strongly, and that attraction is what holds the limestone together. This kind of bonding between ions of opposite charge is called ionic bonding, and it gives limestone its solidity, its weight, its apparent permanence. But ionic bonds, strong as they are, have a vulnerability. They can be disrupted by the right kind of chemistry. When our acidic water, carrying its hydrogen ions, arrives at the surface of a limestone crystal, those hydrogen ions are attracted to the carbonate ions in the rock. A hydrogen ion, which is simply a proton, a bare nucleus with a positive charge, can attach itself to a carbonate ion and convert it into a bicarbonate ion. The calcium ion, now no longer held in place by its partner, is free to drift away into the water. The reaction produces calcium bicarbonate, K2, which, unlike calcium carbonate, is soluble. It dissolves into the water and is carried away. This is the dissolution of limestone. Not a violent process, not a sudden one. Not a violent process, not a sudden one. Grain by grain, iron by iron, the rock gives something of itself to the water passing through it. On a human timescale, it is imperceptible. On a geological timescale, it is one of the most powerful sculptural forces on the planet. But the raindrop is still moving. It has not yet reached the darkness we are heading toward. It is still in the upper layers of rock, still threading through the pore spaces, the tiny gaps between mineral grains that exist even in solid-seeming stone. The movement of water through these spaces is governed by 2 forces. The first is gravity, the gentle, constant insistence of the Earth's mass pulling everything with weight downward. The second is something called a pressure difference, the tendency of water to move from places where there is more of it, pushing from behind toward places where there is less pressure. Together, these 2 forces guide our drop downward and, where the rock allows it, sideways and through. The drop moves slowly. In some rock, through very fine pore spaces, it might travel only a few centimeters in a day. In others, where the pore spaces are larger and more connected, it might move faster. But in most cases, the journey from the surface to the deep rock takes not hours or days, but years. In some geological settings, water that fell as rain during a particular season will not emerge at a spring until several decades later. In the deepest systems, water that is extracted from boreholes today may have last seen the surface sky during the last ice age, 10,000 years ago, when glaciers still covered much of northern Europe and the first human settlements were being built in the river valleys of the ancient Near East. There is something worth sitting with in that, the water moving beneath you right now. Beneath whatever ground is under the building you are in, beneath the streets, beneath the fields. Some of it has been there since before recorded history. It has been moving, patient and unhurried, through the same slow negotiation with rock that our single raindrop is now beginning. Eventually, our drop reaches a depth where something changes. Above this depth, the pore spaces in the rock contain both water and air. The water clings to grain surfaces and fills some gaps, but air occupies the rest. This upper region is called the unsaturated zone, or the Vardos zone. Below a certain depth, however, all of the pore spaces are completely filled with water. There is no more air. The rock is saturated, the way a sponge is saturated when it cannot hold anymore. The upper surface of this completely saturated region is the water table. Our drop crosses that boundary. It enters the saturated zone. It is now, for the first time, in true darkness, surrounded not by the occasional air gap, not by the half-light that filters through thin soil above, but by rock and water on all sides, in a world that has not seen the sun. The drop is held there, still and patient, one small part of a vast body of water moving through stone, going somewhere, going slowly, going in the dark. Water does not simply seep through rock and disappear, given enough time. And the earth has time in quantities almost too large to hold in mind. Water finds a way to make space for itself. The caves that exist beneath limestone landscapes are not accidents. They are the accumulated result of the same chemistry we just followed, replicated billions upon billions of times in the same places over spans of time measured in millions of years. The question worth sitting with is not just that caves exist, but how something as apparently fragile as mildly acidic water carves chambers large enough for a cathedral to stand inside. It begins with a crack, not even a crack, a joint, a hairline fracture in the limestone, left by the slow movement of tectonic plates or by the contraction of rock as ancient seas retreated and pressure was released. But they are enough. Water finds the crack. It seeps in, carrying its dissolved carbon dioxide, carrying its hydrogen ions ready to attack the carbonate ions in the limestone walls. Dissolution begins. The crack widens, not quickly but measurably over centuries. And here is the critical thing, the mechanism that turns a hairline fracture into a river passage. As the crack widens, it allows more water to flow through it. More water means more acid arriving at the rock surface. More acid means faster dissolution. Faster dissolution means the crack widens further, which allows more water, which brings more acid. The process feeds itself, accelerating over thousands of years in what scientists call a positive feedback loop, each step making the next step faster until what began as a fracture invisible to the naked eye has become a passage you could walk through. The rate of this widening is worth thinking about carefully because it illustrates how geological time makes the extraordinary ordinary. In the early stages of cave development, when the crack is very narrow, the water moving through it is in contact with rock along its entire length, and the dissolution happens relatively evenly throughout. But as the crack widens and water begins to flow more freely, something changes in the character of the flow itself. In very narrow passages, water moves in what is called laminar flow, all the water molecules moving in the same direction, in smooth parallel layers like a deck of cards sliding slowly across a table. Laminar flow is gentle but thorough. As passages widen, however, and the speed of flow increases, the water begins to tumble over itself, mixing and churning in what is called turbulent flow. Turbulent water is far more effective at both dissolving rock chemically and removing loosened material physically. It can carry grains of sand and fragments of rock in suspension, using them as natural abrasives to scour the passage walls. This is where a genuine scientific debate sits, one that has been sharpened by recent research. For a long time, the dominant understanding of cave formation emphasized chemical dissolution, the acid dissolving the limestone, as the primary mechanism. The physical scouring by turbulent water was considered secondary. But work by researchers including Cooper and Covington, published in 2020, used detailed computer models to simulate the development of cave passages under different conditions. Their models suggested that physical erosion, the mechanical removal of rock by flowing water and the sediment it carries, the same process that carves river canyons at the surface, plays a more significant role in shaping cave passages than had previously been appreciated. When they ran their simulations with physical erosion included alongside chemical dissolution, the resulting passage shapes matched the shapes of real cave passages more closely than when dissolution alone was modeled. The two processes are not separate sculptors competing for credit. They are partners, each making the other's work more effective. What do they produce, given sufficient time? The answer is best understood through a specific example, and there is no better one than the cave system that lies beneath the Yucatan Peninsula of Mexico. The Yucatan is a vast platform of limestone, built from the accumulated shells and skeletons of marine creatures that lived in shallow tropical seas between roughly 65 and 23 million years ago. When the seas retreated and the land was exposed, the limestone was left open to the chemistry we have been following. Rain fell, carbon dioxide dissolved, carbonic acid formed, and in the limestone beneath the flat, scrubby surface of the Yucatan, a process of dissolution began that has been running ever since. The result is a system of caves and passages so extensive that its full dimensions are still being established. The portion known as Sistema, Sac Acton, a name from the Mayan language meaning white cave system, was confirmed in 2018 to be the longest known underwater cave system in the world, stretching more than 150 kilometers of mapped passage. It was confirmed that year when cave divers working in different parts of the system found the point where two previously separate mapped sections connected, merging what had been called Sistema Sac Acton and the nearby Dos Hoyos system into a single continuous network. 150 kilometers is roughly the distance from London to Birmingham, or from New York City to Philadelphia, but instead of following a surface road, that distance threads through flooded passages in solid rock, sometimes wide enough to swim through freely, sometimes narrowing to gaps that require a diver to remove their equipment to pass. The passages in Sac Acton are flooded today because sea level is higher now than it was during the last ice age, when much of the world's water was locked in glaciers. During the ice age, when sea levels were lower, the Yucatan's cave passages were air-filled, the water table was deeper, and the caves were dry enough for ancient humans to enter. Evidence of their presence has been found, the bones of people who lived, and, in some cases, died in those passages tens of thousands of years ago, preserved by the stable, cool conditions of the deep cave. When the Ice Age ended and glaciers melted, sea levels rose and the caves flooded. The water that fills them now is a mixture of fresh groundwater moving slowly inland from the surface and saltwater intruding from the sea. The boundary between the two, called a halocline, creates a shimmering optical effect visible to divers, a wavering layer where fresh and salt water of different densities meet but do not fully mix. The chambers within the Sac Acton system vary enormously in scale. Some are narrow conduits just wide enough for a human body. Others open into spaces the size of concert halls, their ceilings hung with stalactites, those downward-pointing formations of calcium carbonate that form when water dripping from a cave ceiling loses some of its dissolved carbon dioxide into the cave air, becomes slightly less acidic, and deposits a fraction of its dissolved calcium back as solid mineral. Each stalactite is a record of the same chemistry that dissolved the cave, running in reverse. The water that took calcium away from the walls is, very slowly, giving some of it back, one thin ring of mineral at a time. A stalactite grows at roughly 1 cubic centimeter per year in favorable conditions. The largest stalactites in deep cave systems are tens of meters long. The arithmetic is left to drift through slowly. The chambers and passages of a fully developed cave system like Sac Acton are not random. They follow the original pattern of joints and fractures in the limestone, enlarged along the paths where water moved most freely. They tend to form in particular zones near the water table, where the mixing of fresh water from above and more chemically distinct water from below creates especially aggressive dissolution conditions, a process called mixing corrosion. The result is a three-dimensional maze that maps the ancient hydrology of the landscape above. Every passage a record of where water once moved, every chamber a monument to the patient work of acid and time. Outside, on the flat surface of the Yucatan, the only visible evidence of all this hollow space below is the cenotes, circular holes in the ground where cave ceilings have collapsed, opening shafts of sunlight down into the flooded passages. Town. For now, it is enough to know that they exist, windows, sudden and circular, looking down into the darkness where the water moves. Not all underground water flows through open cave passages. The vast majority of it, the water that fills aquifers, that supplies the wells and boreholes that billions of people depend on for drinking water, that slowly moves through the rock beneath farmland and cities and desert, moves not through hollow spaces, but through the rock itself, through the tiny gaps between mineral grains, through the microscopic network of pores that exists in every sedimentary rock and in many others. Understanding how water moves through these spaces requires thinking carefully about two properties of rock that are related but not the same. The first is porosity. Porosity is simply the fraction of a rock's total volume that is empty space, pores, gaps, voids between grains. Imagine a jar filled with marbles. The marbles are the rock grains, the air between them is the pore space. A typical sandstone might have a porosity of between 10 and 30%, meaning that between 1/10 and nearly 1/3 of its total volume is empty space that could be filled with water. Clay has even higher porosity, sometimes over 50%. Granite, a crystalline rock where mineral grains have grown tightly interlocked, has very low porosity, perhaps 1 or 2%. But porosity alone does not tell you how easily water can move through a rock. For that, you need the second property. Permeability. Permeability measures how well connected those pore spaces are. A rock can have high porosity, lots of empty space, but if the pores are isolated from each other, like bubbles trapped in solid foam, water cannot flow from one to the next. The rock is porous but not permeable. Clay is a good example of this. Clay particles are very small and packed together in a way that creates many tiny pores, giving clay high porosity. But the pores are so small, and the connections between them so narrow that water moves through clay almost impossibly slowly. Clay is, for practical purposes, nearly impermeable, which is why it is used to line the bases of reservoirs and landfills. Sandstone, by contrast, tends to have both reasonable porosity and good permeability. The sand grains are large enough that the gaps between them are wide enough for water to move through relatively freely. Water can flow from pore to pore, finding a connected path through the rock, moving in the direction that gravity and pressure differences push it. The relationship between permeability and flow was given its first rigorous mathematical description in the middle of the 19th century by a French civil engineer named Henry Darcy. Darcy was working in the city of Dijon, designing a water supply system, and he needed to understand how water moved through the sand filters used to purify the city's drinking water. He conducted a series of careful experiments, packing sand into vertical cylinders, running water through them under controlled conditions, and measuring the rate at which water flowed through in relation to the pressure difference driving it. What Darcy found was a clean, simple relationship. The rate of flow through the sand, the volume of water passing through a given area per unit of time, was directly proportional to two things: the difference in water pressure between the top and bottom of the sand column, and a property of the sand itself that he called its hydraulic conductivity. If you doubled the pressure difference, the flow rate doubled. If you used a sand with larger grains and more connected pores, higher hydraulic conductivity, the flow rate was higher for the same pressure difference. This relationship, now called Darcy's Law, is one of the foundational principles of hydrogeology. It has been tested in materials ranging from fine clay to coarse gravel, and it holds remarkably well whenever the flow is slow and orderly, what we earlier called laminar flow. The reason it holds comes down to the physics of water itself. Water is a viscous fluid. It has internal resistance to flow, arising from the same hydrogen bonds between molecules that give water so many of its unusual properties. Hydrogen bonds form because of the polar nature of the water molecule we described in the first chapter. The slightly positive hydrogen ends of one molecule are attracted to the slightly negative oxygen ends of neighboring molecules, creating a loose but persistent network of attractions. When water is forced to flow through narrow pore spaces, the molecules near the walls of the pore are slowed by friction with the rock surface, while molecules in the center of the pore move more freely. The viscosity of the water, its internal friction arising from those hydrogen bonds, means that the velocity of flow varies smoothly across the width of the pore, from nearly zero at the walls to a maximum at the center. Darcy's law is, in essence, a macroscopic description of the cumulative effect of this molecular scale friction playing out across millions of pores simultaneously. The speeds that result from this process are worth dwelling on, because they are so different from anything we associate with the word river at the surface. In a typical sandstone aquifer, water might move at a rate of a few tens of meters per year. That is roughly the length of a bus every 12 months. In tighter, less permeable rock, mudstone for instance, the rate might be a few centimeters per year, 1 centimeter per year, the width of a fingernail in 12 months. Compare that to the flow of water in an open cave conduit, where the same water that has been seeping slowly through rock encounters an open passage and is suddenly unconfined. In a large cave river, water might flow at several meters per second, thousands of times faster than the water creeping through the surrounding rock. The transition from porous flow to conduit flow is one of the most striking contrasts in all of hydrology. And then consider the surface. The Amazon River, the largest river on Earth by volume of flow, moves water at an average rate of roughly 210,000 cubic meters per second at its mouth. That is a number almost too large to picture. But beneath the Amazon basin, a different kind of water movement has been identified. Researchers studying deep boreholes drilled for oil exploration in Brazil noticed in 2011 that water was moving through porous rock formations at depths of around 4,000 meters, more than 13,000 feet below the surface. This deep flow, sometimes informally called the Hamza system after one of the researchers involved, moves through porous rock rather than an open channel. It is, strictly speaking, an aquifer flow rather than a river. Its estimated rate of movement is perhaps a few hundred meters per year, vastly slower than the Amazon above it. Its estimated volume of flow is orders of magnitude smaller than the surface river, but it is vast in extent, moving through rock beneath an area the size of a continent, carrying water that has been underground for a very long time indeed. What both examples illustrate, the slow seep through sandstone and the deep flow beneath the Amazon, is that underground water is not a mirror image of surface water, just hidden. It is something fundamentally different in character. It moves by different rules, at different speeds, under different forces. It carries the memory of rain that fell decades or centuries or millennia ago. It fills spaces that have no banks, no surface, no sky above them, only rock on all sides and the patient, unhurried pressure of water finding its way through. The water table, which we met in the first chapter, is not a fixed surface. It rises when rain is heavy and recharge is plentiful. It falls during dry seasons or when more water is pumped from wells than is naturally replaced. In some places, it is a few meters below the surface. In others, it is hundreds of meters down. Its depth and movement are governed by the same principles Darcy described. by the permeability of the rock, the pressure gradients, the rate at which water arrives from above, and through all of it, the water moves. Slowly, steadily, without any particular hurry, going where the pressure difference and gravity direct it, following paths laid down by the structure of the rock, patient in the way that only something with geological time on its side can afford to be. There is a particular kind of knowledge that changes how you walk through a city. It is the knowledge that beneath the pavements and the underground lines and the buried cables and the foundations of buildings, there are rivers still flowing. Literally, rivers, carrying water, following courses established long before the first stone was laid, still moving today through tunnels of brick or through the same ancient channels they have always occupied, invisible beneath the weight of everything built above them. London is a city built on water, not just the Thames, though the Thames is ancient and central and impossible to ignore, but on a whole network of smaller rivers and streams that once threaded the landscape of what is now one of the world's largest cities. There were rivers in the valleys between the low hills. There were streams running down to the Thames from the north and south. The city that grew over centuries grew around and over these waterways, first using them, then enclosing them, and finally, in the great sanitary reforms of the Victorian era, burying them almost entirely. The River Fleet is the most famous of London's hidden rivers, and its story is worth following in some detail, because it illustrates something about the relationship between cities and the water beneath them that is still being worked out today. The Fleet begins, or rather, its two source streams begin, on the high ground of Hampstead Heath in North London, where springs emerge from the sandy deposits overlying the clay. The two branches flow southward, joining somewhere near what is now the neighbourhood of Camden, and the combined river runs south through the valley that is still visible if you know to look for it. The dip in the land through which Farringdon Road and King's Cross Road run, a valley too regular and too persistent to be explained by anything other than a river that made it. The Fleet runs down through what are now Clerkenwell and Farringdon, under the Holborn Viaduct, built in the 1860s specifically to bridge the Fleet Valley, and enters the Thames near Blackfriars Bridge. For most of London's early history, the Fleet was a working river. It was wide enough, in its lower reaches, to be navigable by small boats. Wharves lined its banks. Goods were unloaded there. Mills operated on its water. But as the city grew denser and more industrial, the Fleet became something else. The tanneries and slaughterhouses and dye works that clustered along its banks discharged their waste into it. The river became foul, not just unpleasant but actively dangerous, a source of disease in an era before anyone understood the connection between contaminated water and cholera. The smell alone, in summer, was reportedly enough to be noticed at a considerable distance. The solution, arrived at gradually through the 17th, 18th and 19th centuries, was to cover the river, first in its lower reaches, then progressively further upstream. The Fleet was vaulted over, built above with brick arches, enclosed, hidden. The work was done in stages by different authorities over more than 2 centuries. By the time Joseph Bazalgette's great Victorian sewer system was constructed in the 1860s, the Lower Fleet had been incorporated into the new drainage network, its channel serving as the main conduit for one of London's principal sewers. Today, the River Fleet flows through a tunnel of Victorian brickwork beneath Farringdon Street, carrying a mixture of rainwater runoff and, in the older sections of the sewer system, other matter besides. It is still moving. It still reaches the Thames. It still follows, precisely, the course it has always followed, because rivers do not reroute themselves simply because a city has been built above them. This last point matters more than it might seem. The Fleet and London's other hidden rivers, the Westbourne, which flows through a large iron pipe visible above the platforms of Sloane Square Underground Station, the Effra, which runs beneath Brixton, the Walbrook, which gave its name to a street in the city. These rivers have not been neutralized by being buried. They have been contained, But containment is not the same as control. When rainfall is heavy enough that the river's flow exceeds the capacity of the tunnels and culverts built to carry them, the water goes where water always goes. It follows the path of least resistance back to the surface. The flooding that affects certain streets and underpasses in London during heavy rain is not random. It follows, with remarkable fidelity, the courses of the buried rivers beneath those streets. The water remembers where it is supposed to be. London is not unusual in this. New York City has dozens of buried streams and rivers. The Minetta Brook still flows beneath Greenwich Village, its course detectable by the way basements in certain blocks flood during heavy rain, by the springs that emerge unexpectedly in construction excavations. Paris has its own network of hidden waterways, some incorporated into the famous catacombs and sewer system. Moscow, Seoul, Tehran, Mumbai. The list of cities built over buried rivers is essentially a list of the world's great old cities, because all of them grew beside water, and all of them eventually grew over it. Seoul offers a different kind of story, though not of burial but of recovery. The Cheongyekan stream runs through the center of Seoul, threading between modern buildings and under pedestrian bridges for a distance of about 11 kilometers through the heart of the city. Today, it is a genuine public waterway, a place where people walk along its banks in the evening, where children wade in summer, where the sound of moving water softens the noise of a dense urban environment. But for nearly half a century, it did not exist in this form. The Cheongyekan was covered by a concrete road in the 1950s as the city rebuilt after the Korean War, and then covered further by an elevated expressway in the 1970s. For decades, the stream was invisible, buried, forgotten, its existence known mainly to engineers and historians. In 2003, the city of Seoul made a decision that was, at the time, considered by many to be extraordinary. It would remove the expressway, excavate the stream's course, and restore the Cheongyekan to the open air. The project took 2 years and was completed in 2005. What emerged was not simply a restored stream. The natural flow of the Cheongyekan had been so reduced by the impermeable surfaces covering its catchment that the restored channel required supplemental water pumped from the Han River to maintain a reasonable flow. But the result was, by most measures, a transformation. The urban heat island effect in the surrounding area decreased, biodiversity increased, air quality improved in the immediate vicinity, property values along the stream rose. The Cheongyekan became a model for what is now called river daylighting, the deliberate restoration of buried urban waterways to the surface. The movement is growing. Cities in Europe, North America, and Asia are examining their buried rivers not just as engineering problems to be managed, but as potential assets, as corridors for biodiversity, as natural flood management systems, as public spaces with a quality of presence that no designed landscape can quite replicate. There is something quietly important in this shift. The buried rivers were not eliminated. They were hidden, managed, redirected. But they continue to flow. They continue to shape the ground above them in ways that the city's engineers had to account for in every subsequent generation of construction. And now, in city after city, there is a growing recognition that the water beneath the streets is not a problem to be suppressed, but a feature to be understood, and, where possible, restored to the light it was taken from. The river fleet, for now, remains in its Victorian tunnel, but there are proposals, discussed with increasing seriousness, for at least partially daylighting it, opening sections of its course to the sky, letting the water be seen again. Letting the water be seen again. The river has been plowing in the dark for more than 2 centuries. A little longer is nothing, measured against the time scale of water. In the deep cave rivers of the Yucatan, in the flooded limestone passages of the Mendip Hills in Somerset, in the underground streams of the Dinaric Karst in the Balkans, there are creatures that have never seen light. Not because they are nocturnal, not because they shelter from the sun during the day and emerge at night, but because the concept of light is entirely outside their experience. They were born in darkness, as their parents were, and their parents' parents, and their ancestors for hundreds of thousands of generations before them, in water that has not touched a surface exposed to sunlight for longer than our species has existed. These are the troglobites, a word from the Greek for cave dwellers, and they are among the most biologically fascinating organisms on Earth, not for what they have gained, but for what they have lost, and for what that loss reveals about how evolution actually works. Eyes are expensive, not in any monetary sense, but in the deep biological economy of energy and resources that every living organism must balance. Building an eye requires the coordinated development of dozens of different cell types: photoreceptor cells, lens cells, corneal cells, the neurons that carry signals from the eye to the brain, the blood vessels that supply oxygen and nutrients to all of these. Maintaining an eye requires ongoing metabolic investment. The photoreceptor cells must continuously regenerate the light-sensitive pigment molecules they use to detect light. The neural pathways from eye to brain must be kept active. The whole structure must be protected from infection and damage. In an environment where light is available, this investment pays for itself. The information provided by vision is worth the cost. But in an environment of permanent, absolute darkness, where no light has ever penetrated, an eye provides no information at all. It is metabolic expenditure without return. Evolution does not consciously decide to remove useless structures, but mutations that disrupt eye development are not eliminated by natural selection if the eyes were providing no advantage anyway. Over many generations, these mutations accumulate. The developmental pathways that build eyes become progressively disrupted, and the energy that was spent on eye development is gradually redirected through the accumulation of mutations that benefit other systems towards senses that do provide useful information in the dark. What is remarkable is that this process, the gradual loss of eyes in populations isolated in cave environments, has happened independently in an enormous number of different evolutionary lineages. Blind cave shrimp, blind cave beetles, blind cave salamanders, blind cave spiders. In each case, the same environmental pressure has produced the same result through independent evolutionary paths. The blind cave fish of the Yucatan cenotes, several species of the genus Astyanax, have been particularly well studied. Their surface-dwelling relatives have fully functional eyes. The cave populations have vestigial eyes, structures that begin to develop in the embryo but then degenerate, leaving adult fish with small, non-functional eye remnants beneath the skin. Genetic analysis has shown that this degeneration is not caused by a single mutation, but by changes in multiple genes, each contributing a small effect accumulated over the roughly 10,000 years since the end of the last ice age isolated these fish populations in their flooded cave systems. In compensation for the loss of vision, the lateral line system, a network of sensory cells along the sides of the body that detects pressure changes and water movements, is dramatically enhanced in cave-adapted fish compared to their surface relatives. The number of sensory organs in the lateral line is higher, their sensitivity is greater, and the area of the brain devoted to processing their signals is correspondingly enlarged. The fish navigate, find food, and avoid obstacles through an exquisitely sensitive perception of the water movements around them, a sense we have no direct equivalent for and can only imagine. The food web in a cave river ecosystem is built on a completely different foundation from anything at the surface. Surface ecosystems are ultimately powered by photosynthesis, the conversion of sunlight into chemical energy by plants, algae, and photosynthetic bacteria, which then forms the base of every food chain. In a cave river, there is no photosynthesis. The energy that sustains life there comes from two sources. The first is the slow rain of organic matter from above, Dead leaves, animal droppings, the bodies of insects and other creatures that fall into cave entrances or wash in through sinkholes, carried down by water percolating from the surface. This material is broken down by bacteria and fungi, and the resulting nutrients support small invertebrates, cave shrimp, amphipods, isopods, the tiny crustacean relatives of woodlice, which in turn support larger predators. The second energy source is chemosynthesis, a process by which certain bacteria extract energy not from sunlight, but from chemical reactions, particularly the oxidation of compounds like hydrogen sulfide or methane. In some cave systems, particularly those in contact with geological sources of these compounds, chemosynthetic bacteria form the base of a food web entirely independent of the surface world. The Mobile Cave in Romania, discovered in 1986 and sealed from the surface atmosphere for perhaps 5 million years, contains an ecosystem of approximately 50 species: spiders, leeches, water scorpions, isopods, all ultimately sustained by chemosynthetic bacteria in the cave's warm, sulfurous water. It is one of the most isolated ecosystems on Earth, a reminder that life does not require sunlight, only chemistry. The British cave systems of the Mendip Hills in Somerset, Wookey Hole, Swildon's Hole, the caves of the Cheddar Gorge, host their own adapted communities, less dramatic than Mobile Cave, but no less remarkable in their way. Freshwater shrimp of the species, Gammarus polex, populate the cave streams, showing some degree of depigmentation, their bodies becoming paler than their surface relatives, another energy-saving adaptation in a world where pigment serves no protective function against ultraviolet light that never arrives. Cave-adapted flatworms, cave-adapted amphipods, the rare and elusive cave pearl, a smooth sphere of calcium carbonate that forms when water drips onto a small grain of sediment and slowly coats it in mineral layers, rotating it over centuries until it becomes a perfect sphere. All of these are features of a world that has been developing in isolation for longer than we can easily imagine. But these ecosystems, ancient and adapted as they are fragile in a way that their surface counterparts are not. A field on the surface of a karst landscape is connected to the cave rivers beneath it through the same network of pores and fissures that the water uses to travel down. A herbicide applied to that field will dissolve into rainwater and begin moving downward. A fuel spill, a burst septic tank, a leaking agricultural storage facility. Any of these can introduce contaminants into the karst drainage network. And because karst systems can transmit water relatively quickly, sometimes at rates of hundreds of meters per day through large conduits, that contamination can arrive in a cave river far from the surface source, sometimes weeks or months later in a concentration that was diluted during its journey but not eliminated. The creatures in that cave river have no mechanism for detecting the contamination before it arrives, no way to move to cleaner water, no evolutionary preparation for synthetic chemicals that did not exist when their lineages were isolated. The darkness that protects these creatures from the pressures of the surface world is also the darkness that makes them invisible to the surface world's consequences. Long before anyone had the tools to measure the pH of rainwater or model the dissolution of calcium carbonate, people noticed something that demanded explanation. Water disappeared. It fell into holes in the ground and was not seen again. Springs emerged from cliff faces with no visible source, pouring cold, clear water from solid rock. Rivers ran to the edge of a limestone plain and vanished. In places, the ground itself opened, great circular holes dropping into darkness with the sound of water far below. These observations were not ignored. They were absorbed into the deepest layers of human meaning, making into the myths and religious geographies that every culture uses to organize its understanding of the world. And in culture after culture, across continents and millennia, the water that went down into the earth became associated with the same things: death, the underworld, forgetting, the passage between the living and the dead. It is difficult to know whether this was coincidence or something deeper, whether there is something in the act of watching water disappear into darkness that speaks to something universal in human experience. The Greeks were particularly systematic about the geography of their underworld, and their underworld rivers are worth examining not just as mythology, but as a kind of phenomenological record, an attempt to describe, in narrative form, the behavior of actual water in a landscape rich with karst features. Greece and the surrounding Aegean region sit on limestone. The Peloponnese, Epirus, Crete, much of the Greek mainland, these are karst landscapes full of sinkholes, disappearing rivers and springs that emerge with no obvious surface source. The ancient Greeks lived with this hydrology daily. They saw rivers vanish into the ground. They saw springs appear from cliffsides. They knew that water moved through the rock beneath their feet, even if they had no framework for understanding how. The river Styx, the river that separated the world of the living from the realm of the dead, was not purely imaginary. There is a real waterfall and stream in the mountains of Arcadia, in the northern Peloponnese, called the Mavroneri, which was identified in antiquity as the physical location of the Styx. It falls from a high cliff face in a thin, dramatic stream, and the water was considered so cold and so strange it was said to dissolve any vessel except one made from a horse's hoof, that it carried an aura of the supernatural. The spring that feeds it emerges from rock, as all karst springs do, with no obvious explanation. Water from nowhere, cold and inexplicable, and issuing from the earth itself. The river Lethe, the river of forgetfulness, whose waters cause the dead to forget their mortal lives before their souls were reborn, has a different and more intimate quality. The Lethe was said to flow around the cave of Hypnos, the god of sleep, in the deepest part of the underworld. Souls drank from it and forgot. What is worth noticing is that this mythological river does something that underground water actually does. It carries away the past. The calcium ions dissolved from limestone are carried away and never return to the rock from which they came. The water that falls as rain and disappears into the earth carries with it the chemical signature of its surface journey, the carbon dioxide, the organic acids, the memories of the soil it passed through, and emerges, eventually, changed, transformed by its passage through the dark. The Lethe is, in one reading, a mythological description of what water actually does when it goes underground. The Phlegethon, the river of fire, is stranger, a river of flame that burned without consuming, flowing through the underworld. Some scholars have connected it to the volcanic features of the Greek landscape, the hot springs and sulfurous gases that emerge from the ground in geologically active areas. Hot springs, after all, are simply groundwater that has circulated deep enough to be heated by the Earth's internal warmth and then risen back to the surface. The Phlegethon may be a mythological encoding of the observation that water emerging from the ground can be hot, can carry sulfurous smells, can seem to come from a place that is geologically alive. Moving east, the ancient Indian textual tradition contains a river called the Saraswati, described in the oldest Sanskrit texts as a great river flowing through the northwestern plains of the subcontinent. The Saraswati appears in the Rig Veda, one of the oldest religious texts in the world, composed perhaps 3,500 years ago, as a mighty, sacred river described with the same reverence given to the Ganges. It was described as flowing underground, hidden from sight, joining the Ganges and Yamuna at their confluence at Prayagraj in a mystical, invisible union. For a long time, this was treated as purely mythological, but geological research conducted in the 20th and 21st centuries has found evidence of something real beneath the apparent legend. Satellite imagery and ground-penetrating surveys have identified buried river channels, paleo-channels, the technical term for ancient riverbeds now filled with sediment, beneath the plains of Haryana and Rajasthan in northwestern India, following a course consistent with the descriptions in the ancient texts. The channels suggest that a large river did once flow there and that it dried up and disappeared, not underground in the way karst rivers disappear, but through a combination of tectonic shifts that diverted its source rivers and climatic changes that reduced rainfall in the region, perhaps around 4,000 years ago. The river did not go underground in the literal hydrogeological sense, but the observation that a great river had vanished, that it was there and then was not, was real. The mythological explanation that it flowed unseen beneath the surface was a genuine attempt to make sense of a genuine disappearance. And then there is the Yucatan, where the relationship between surface and underground water took a form so dramatic and so direct that it became the organizing principle of an entire religious and cosmological system. The cenotes of the Yucatan are the places where the cave ceiling has collapsed, opening windows from the surface down into the flooded cave passages below. Some are open pools, their edges fringed with tree roots that reach down through the limestone to the water. Others are partially enclosed, lit from above by a shaft of light that falls through the opening and illuminates the water in shades of green and blue. The water in them is the same water that fills the Sac-Acton system, the same ancient, slow-moving groundwater that has dissolved its way through the limestone over millions of years. For the Maya, who built their civilization on the Yucatan Peninsula, cenotes were not simply water sources, though they were that too. In a landscape with no surface rivers and very little surface water, cenotes were the primary source of fresh water for entire cities. They were also sacred thresholds, the place where the visible world ended and the invisible world began, the entrance to Xibalba, the Mayan underworld, a place of rivers and darkness and the trials of the dead. Offerings were placed in cenotes. In some cases, the cenotes received more than offerings. The sacred cenote at Chichen Itza, one of the great Mayan cities, has been the subject of careful archaeological excavation. Objects of gold, jade and copal incense were found there, along with human remains, evidence that the cenote was a place of sacrifice and ritual deposition, a physical point of contact between the human world and the world below. What is striking about the Mayan relationship with cenotes is how accurately it maps the actual hydrology. The cenotes really are windows into an underground river system. The water that enters a cenote really does connect to a vast, dark, interconnected network of passages extending for hundreds of kilometers in every direction. The underground world really is a world of rivers. The Maya, who had no scientific instruments and no way to explore the flooded passages below, nonetheless understood. Through observation, through the evidence of their own water supply, through whatever direct exploration was possible in the dry passages of the Ice Age, that the water went somewhere, that it flowed through the rock in the dark, that the cenote was a threshold, a place where two worlds met. Myth, at its best, is not ignorance dressed up in story. It is observation that has been given a form capable of being remembered and transmitted and felt. The underground rivers of human mythology are the underground rivers of geology, seen from the surface, by people who understood that something was happening in the dark, even if they could not follow it all the way down. There is a particular challenge at the heart of hydrogeology that does not apply to most other sciences. The thing being studied is hidden. You cannot look at a subterranean river the way you can look at a surface river. You cannot fly over it, photograph it, measure its width from the bank. The water is inside the rock, moving through spaces that, in most cases, no human has ever entered, and no instrument has ever directly reached. The science of underground water is, in a fundamental sense, a science of inference, of figuring out what is happening in the dark from the evidence it leaves at the surface. The methods that have been developed to do this are ingenious in ways that reward careful attention. The oldest and most direct is the tracer dye experiment. The logic is simple. If you want to know where water goes after it disappears into the ground at one point, you put something into it that you can detect when it comes out, and then you wait. In karst hydrology, the tracers most commonly used are fluorescent dyes, synthetic compounds that, when dissolved in water at extremely low concentrations, glow brilliantly when illuminated with the right wavelength of light. The most widely used is a compound called uranine or fluorescein, which produces an intense green-yellow fluorescence. A small quantity, perhaps a kilogram, dissolved in a few hundred liters of water, is poured into a sinkhole or a cave entrance. Passive detectors, small packets of activated charcoal that absorb the dye from any water flowing past them, are placed in springs, wells, and streams throughout the surrounding area. The detectors are collected and analyzed in a laboratory days, weeks, or months later. What the dye reveals can be extraordinary. In karst systems, the connection between a sinkhole and the spring where the water emerges can be direct and fast. The dye may travel several kilometers in a matter of days, moving through large open conduits at speeds that bear no relation to the slow pour. In other cases, the dye takes weeks to appear and appears at multiple springs simultaneously, suggesting that the water has split along multiple pathways through a complex three-dimensional network. In some experiments, dye introduced at one location has been detected at springs more than 20 kilometers away, the water having traveled unseen through the rock between. One of the classic tracer experiments in British speleology, the study of caves, was conducted in the Mendip Hills of Somerset, where the hydrology of the limestone is complex and the connections between swallet holes and springs are not obvious from the surface geography. Dye introduced into different swallets was tracked to different springs, revealing a drainage pattern that bore no relationship to the surface topography. Water that disappeared at one point emerged not at the nearest spring, but at one several kilometers away in a direction that the surface landscape gave no hint of. The underground drainage network had its own logic, following the structure of the limestone rather than the shape of the hills above. The limitation of tracer dyes is that they only tell you about the specific connection between the point of injection and the point of detection. They do not give you a three-dimensional map of the passages in between. Electrical resistivity tomography, a technique that builds an image of what lies beneath the surface by measuring how rock and water respond to electrical current, works on the principle that different materials conduct electricity differently. Water, particularly water containing dissolved minerals, as all groundwater does, having spent time dissolving the rock around it, conducts electricity much more readily. By passing electrical current between electrodes placed on the surface and measuring the voltage at other points, it is possible to calculate the electrical resistivity of the rock at different depths and locations. Low resistivity indicates water-saturated rock. High resistivity indicates dry rock or air-filled voids. The technique was originally developed for mineral exploration. Geologists looking for ore deposits found that the electrical properties of mineralized rock differed from the surrounding country rock in ways that could be detected from the surface. Applied to hydrogeology, it allows researchers to map the water table, to identify zones of high water content, and in some cases, to detect large cave passages filled with water by the anomalously low resistivity of the water-filled void surrounded by more resistive limestone. It is not a perfect technique. The resolution decreases with depth, and the interpretation of the data requires considerable expertise and judgment, but it has become one of the standard tools for non-invasive investigation of the subsurface. The most recent and arguably most powerful development in underground water mapping is the application of machine learning to the vast datasets of groundwater measurements that have accumulated over decades of drilling, monitoring, and research. A study published in January 2026 by researchers at Princeton University and the University of Arizona represents perhaps the most ambitious application of this approach yet attempted. The researchers assembled over 1 million direct measurements of groundwater depth from monitoring wells, boreholes, and other sources from across the continental United States and combined them with detailed information about regional climate, geology, topography, and land use. They then trained machine learning models, algorithms that find patterns in large datasets and use those patterns to make predictions in areas where direct measurements are absent, to predict groundwater depth at a resolution of approximately 30 meters across the entire continental United States. The resulting map revealed something that coarser previous estimates had missed. The total volume of groundwater in the continental United States is approximately 306,000 cubic kilometers. To give that number some scale, the combined volume of all 5 of the Great Lakes is roughly 22,000 cubic kilometers. The groundwater beneath the continental United States contains more than 13 times the volume of all the Great Lakes combined. And the map showed that roughly 40% of the land area of the continental United States has groundwater within 10 meters of the surface, far more than previous estimates had suggested, and with implications for everything from flood risk to agricultural water availability to the stability of building foundations. What is perhaps equally important about this study is what it honestly acknowledges, that even with 1 million data points and sophisticated machine learning, the map is a prediction, not a measurement. In areas where direct measurements are sparse, much of the American West, for instance, the model's predictions carry greater uncertainty. The resolution of 30 meters is unprecedented for a national-scale map, but 30 meters is still a coarse grid compared to the scale of individual aquifer features, the full 3-dimensional structure of most groundwater systems. There is an honesty in this that is worth appreciating. Science, at its best, is not a process of accumulating certainty, but a process of progressively refining uncertainty, of knowing more precisely what we do not know. The map of underground water is better today than it has ever been. It will be better still in 10 years. But it will never be complete in the way that a map of the surface can be complete, because the surface can be seen and the depths cannot. The ground beneath any given place conceals more than it reveals, and the water moving through it follows paths that remain, in most of the world, largely uncharted. This is not a failure of science. It is a reflection of the genuine depth of the world. The underground is vast and old and patient, and it does not give up its secrets quickly. The scientists who study it have learned to be patient too, to work with incomplete information, to draw careful inferences, to follow the dye where it leads, and accept that the passages it traveled through are still, for now, beyond reach. The most thorough map of the world's underground water that will ever exist is still being drawn. It may never be finished. The water moves on regardless. We have come a long way tonight, from a single raindrop falling through air already changed by its chemistry, down through soil and stone, into the saturated darkness of the deep rock. Through the slow carving of cave passages over millions of years, the mechanics of flow through pore spaces too small to see, the buried rivers of great cities still following their ancient courses beneath the weight of everything built above them. Through the creatures that have lived so long in darkness that light has become unnecessary, the myths that named the underground rivers and made them sacred, the instruments and algorithms that attempt to map what cannot be seen. All of it has been about the same thing, really, about what happens beneath the surface, about the enormous, patient, largely invisible processes that shape the world while no one is watching. You are doing something similar right now. The science of sleep is, in many ways, a science of the underground. The most important things that happen during sleep happen out of awareness, in the deeper structures of the brain, following processes laid down long before conscious thought was possible. While you lie still, your brain is not resting in any simple sense. It is working, sorting through the events of the day, deciding what to consolidate into long-term memory and what to allow to fade, processing emotional experiences in the relatively safe chemistry of sleep rather than in the charged environment of waking. The hippocampus, A structure deep in the brain, shaped something like a seahorse, essential for the formation of new memories, replays the day's experiences during sleep, transferring their content to the slower, more stable storage of the cerebral cortex. This process is gradual and unhurried. It happens in the dark. It does not require your attention or your direction. The brain during sleep moves through cycles of different electrical activity, measured in the oscillations of voltage across neural membranes, the rhythmic firing and quieting of billions of neurons working in loose coordination. In waking, these oscillations are fast and varied, reflecting the constant demands of perception and thought. As sleep deepens, the oscillations slow and become larger and more synchronized. Slow waves that wash across the cortex in rolling patterns, like the groundswell of a deep ocean rather than the choppy surface of a busy harbor. These slow waves are the signature of deep sleep, the stage during which the brain's glymphatic system, a network of fluid-filled channels surrounding the brain's blood vessels, only fully described in the scientific literature in 2013, becomes most active, flushing metabolic waste products from the brain tissue. The word glymphatic joins glial, referring to the non-neuronal support cells of the brain, with lymphatic, referring to the body's waste clearance fluid system. In waking, the glymphatic system works slowly. In deep sleep, the channels widen and the flow of cerebrospinal fluid through them increases dramatically, carrying away the accumulated metabolic debris of the day's neural activity. The brain, like the limestone landscape, does its most important housekeeping in the dark, through slow, fluid movement, unseen. The sound of water has a particular relationship with this process. Researchers studying the effects of natural sounds on the resting brain have found that steady, non-threatening auditory patterns, the kind produced by a stream moving over stones, or rain falling on leaves, or water seeping through rock into a quiet underground pool, tend to guide the brain's electrical activity towards slower, broader oscillations. The mechanism involves the brain's threat detection systems, which are ancient and always partially active, even in sleep. Sudden sounds, a sharp crack, a voice calling out, an unexpected noise that breaks a pattern of silence, activate the amygdala, a pair of almond-shaped structures deep in the brain that process emotional significance and coordinate the body's response to perceived threats. The amygdala can pull the brain back toward waking from the edge of sleep, even when the conscious mind does not register the sound as threatening. Water sounds work differently. They are continuous but not monotonous. They vary constantly in detail. The pitch and rhythm of a stream change moment to moment, but they vary within a pattern that the brain quickly learns to recognize as non-threatening. There is nothing in the sound of water that signals danger. Flowing water, in the evolutionary context in which the human brain was shaped, meant proximity to a reliable water source, and reliable water sources were places of relative safety, places to camp, places to rest. The steady murmur of water is, in the deepest sense, a signal that nothing is wrong. The threat detection systems of the brain, finding nothing in the sound that requires action, ease their vigilance. The oscillations slow. The slow waves begin to roll. This is the same principle that underlies what researchers call pink noise, a specific distribution of sound frequencies in which lower frequencies carry more energy than higher ones, producing a sound that is richer and warmer than the flat hiss of white noise. Natural water sounds, streams, rain, the soft movement of water over stones, tend to have a pink noise character. Studies have found that exposure to pink noise during sleep increases the amplitude of the slow oscillations associated with deep sleep, and that people exposed to it show improved performance on memory consolidation tasks the following day, suggesting that the deeper sleep facilitated by the sound has enhanced the overnight processing of the previous day's experiences. The water is not just pleasant to listen to, it is doing something. Picture the raindrop again. the one we followed in the first chapter, falling through air already rich with carbon dioxide, becoming mildly acidic before it touched the ground, entering the soil, beginning its slow negotiation with the limestone below. It is somewhere in the rock right now, or rather, it has been somewhere in the rock for years, for decades, perhaps for centuries, depending on where we imagine it fell. It is moving through pore spaces too small to see, carried by gravity and the gentle pressure of the water behind it, dissolving a grain here, a fraction of a grain there, carrying the dissolved calcium bicarbonate in solution, going deeper. It does not know it is doing this. It has no awareness of the journey. It simply moves, because the forces acting on it direct it to move along the paths that the rock allows, at the pace that the permeability permits. It is patient in the most absolute sense. Patient, not because it is choosing patience, but because it has no relationship with time at all. It is simply water, moving through stone, in the dark, going where it has always been going. There is something in that image that is worth carrying into sleep with you, not as a lesson, not as a metaphor to be analyzed, but simply as a presence, the water beneath you, beneath whatever ground is below the place where you are lying, is moving right now, has been moving through the night, through all the nights before this one, through nights before any human was alive to notice. It moves through the dark without effort, without resistance, without any need to understand the path or see the destination. It simply goes. You don't need to understand the path either. You don't need to see where tonight is going. The slow waves are already beginning if you let them. The broad, rolling oscillations of a brain that has decided, for now, that nothing requires its attention. The glymphatic channels are widening in the deep tissue of your brain, the fluid beginning to move, the quiet housekeeping of sleep beginning its unhurried rounds. Your body knows what to do in the dark. It has always known. These are ancient processes laid down over millions of years of evolution, running in you the way water runs through limestone, without needing to be directed, without needing to be watched. The day is already distant. It will be there tomorrow in whatever form it takes. But right now, in this quiet, in this darkness, there is only the slow movement of things that do not need the light, the water in the rock, the fluid in the deep channels of your brain, the slow waves rolling. Let them take you. You have been moving toward this all day, the way water moves toward the saturated zone, steadily, without drama, following a gradient that was always going to lead here. Down into the quiet, down into the dark, down into the patient, unhurried deep. Well,